So we are into the fourth day of this FTP, and I already had introduced Professor Venkatesh Raman. Is it working? The day before yesterday, we all were fortunate to hear his wonderful lecture on dynamic programming. So he's here with us today again to talk about the NP-Completeness, the various complexity classes P and NP. So please be interactive. Thank you.
And thank you for coming again. So today we will talk about an important open problem in computer science and in foundations of mathematics in general. So to build towards that, let's take stock of the problems you have looked at in the last few lectures and the kind of algorithms we saw, right? So we had probably seen many times sorting, where you want to arrange a sequence in ascending order or descending order, and if you have n elements, we know that we can do it in n log n time. Okay? There is a big O which you've seen finding the median. Anybody remembers how much time it takes? This is Sayan Bhattacharya would have done this application of divide and conquer. It's a nice, one of the classical algorithms. You are given a sequence of n numbers. You want to find who's the element, what is the element which is in the middle of the list after you sort it. And the big open problem at that time in 1970s was, can you actually do without sorting? Right? One way to do it is to sort it and take the middle element, that's n log n time, and the powerful application of divide and conquer actually gives you an order n algorithm. We talked about, or I talked about, longest common subsequence. That takes something like mn time. There are two sequences of length m and n, and you want to find the longest common subsequence. The dynamic programming algorithm takes mn time. I'm going to write more things. Shortest path, all pair, single path, single source, single terminal. They're all taking something like an n cube time. I don't know what more do you saw. Max flow. Roughly n square, n cube. If you have a network on n vertices, you can list down the running time of these problems. I mentioned to you the traveling salesperson problem, where you have a given a network where there are weights on the edges, and you want a cycle that visits every vertex exactly once, come back to the starting point, and you want to find the shortest cycle. And remember the running time. So there's a brute force algorithm we saw, which we said try all permutations of 1 to n. That was like an n factorial algorithm. And then we went through, okay, dynamic programming can give you something like 2 to the n. Okay. So dynamic programming gave you 2 to the n times n squared. Let's look at a couple of more problems, and which we will come across in today's session. And this is a problem in Boolean logic. Let's call it SAT. So the input is, you have a formula. The formula looks like this. Okay, so and of R's. Okay, so you would have all seen something like this in discrete math course or logic course. It's the formula in conjunctive normal form. That's what it is, because this is called conjunction and these are called disjunctions. So you have R of a bunch of variables, and this is a clause, this is a clause, this is a clause, and you have a collection of clauses. This is an input. Okay? The input, you have a formula which has some variables, x1, x2, x3, xn are variables. You have some clauses, and the input is a conjunction of these clauses. And the question we are interested in, is this satisfiable? What does that mean? Is there an assignment of 0, 1 assignment of these variables such that every clause is satisfied? Okay, what does that mean? I can satisfy this clause by setting x1 to 1 or x5 to 1 or x2 to 0. Okay? That's what it means by satisfying a class, because it's an OR of these variables, and every variable gets a value 0 or 1, true or false, and I can satisfy this clause if I can set this to 1 or set this to 1 or set this to 0. But the problem is not to satisfy each clause one by one, you want to simultaneously satisfy all the clauses, right? So if I just go and set x2 to 0, then it's going to affect some other clause. Because this clause, then you need some other variable to satisfy this clause. So the question here is, can you come up with some 0, 1 assignment for this set of variables so that every clause is satisfied? So if this is the entire formula, it's trivially satisfiable. You can set x1 to 1, x3 to 1, and x2 to 1, for example. And for the remaining variables, do whatever you want, doesn't matter, you can satisfy this. Okay, so this is the problem. You want to come up with a general purpose algorithm for this problem, where the algorithm takes as input a Boolean formula like this, and finally the algorithm should look at the formula, do some computation, come back and say, yes, it is satisfiable, or no, it is not satisfiable. Okay. Can you think of again a brute force algorithm for this problem? I was telling you about brute force algorithm. We saw that for TSP, something like n factorial. So if I give you a Boolean formula, I want a method, an algorithm, which will always come back and tell correctly whether it is satisfiable or not. I don't care about the running time. It can be very terrible, bad, dumb algorithm. Can you tell me an algorithm? What would you do? Try all assignments of 0 and 1. So I have this x1 to xn. I set all of them 0, and then I go back. See, once you fix an assignment, it's not very hard to check whether the formula is satisfied by that assignment or not. So take one assignment and then go to this formula and run through and see whether it is satisfied. If yes, you are done, great, done. Otherwise, change some 0 to 1 and try it again. If not, keep trying all possible assignments. How many 0, 1 assignments are there? 2 power n assignments, because every variable gets 2 values. There are n variables. So this is a 2 power n algorithm. Okay, so this problem has a 2 power n algorithm. There may be better algorithms. We'll come back to it. But for now, here is an algorithm which takes 2 power n time. There is an algorithm for TSP which takes about something like 2 power n times n square. Let me write down a couple of more problems. We'll get to it. So that's the continuation of this side. So I give you a graph, minimum vertex cover. Or let's say max click. So I have a graph like this. So it's an 8 vertex graph, this example. I want to, what is a click? Click in the graph is a set of vertices which are mutually pairwise adjacent. Okay. It's a subset of vertices such that any pair of them has an edge. Okay. So one is interested in, given an arbitrary graph, find the maximum click in the graph. So what is the maximum size click in this graph? I want a subset of vertices such that there is an edge between every pair of them. So what is the maximum size click? All the edges. No, this is the graph. Graph is given to you. I give you this input graph. I want some subset of vertices. I don't want all the vertices. Maximum sized subset of vertices such that in that subset there is an edge between every pair of them. Okay, which three? 2, 3, 8 is a click because there is an edge 2, 3, there is an edge 3, 8, there is an edge 2, 8. Yes, so 2, 3, 8 is a click. Is that the maximum size click? What is the maximum? You saying no? Why? Give me a larger click. 1, 2, 3, 8. Yeah. 1, 2, 3, 8 is also a click because there is 1, 2, I think, I don't know, I haven't checked it. There is 1, 2, there is 1, 8, there is 1, 3, there is 2, 8 and 2, 3, and there is 8, 3. So 1, 2, 3, 8 is a click of size 4. Okay. Is there a larger size click? Okay. In such a small example already, it's not that easy to figure this out. Okay, so this is algorithmic question now we have. I give you an arbitrary graph in the form of an adjacency matrix, adjacency list, something like that. And I want to find what is the largest size click in the graph. This is again, all of these problems are pretty important practical problems. It's not some type problem. They are all important practical problems. Now, what would be a brute force algorithm for this? Okay, try all what? You're using the word combination in a loose sense, but yeah, I mean that's the idea. But try all what? Subsets. Try all subsets of vertices because the answer you are looking for is a subset, right? So pick a subset. Check whether there is an edge between every pair of them. Okay, so if you pick a subset of size k, you just have to check some k square edges. And if the answer is yes, good, okay, I got one click. Try all of them and pick the one which is the maximum size, and that's at least one sure brute force algorithm. I mean, always is good to start with such a benchmark thing and see if we can improve it. How much time will that take? 2 power n subsets, and then maybe something like an n square to check for these edges. Okay, so we have seen a lot of problems whose running time is something like n square, n log n, n cube kind of problems. And we have a set of problems where the algorithms have exponential, n is on the exponent. Okay. Now, but you can ask, okay, but this is one algorithm. Is there a better algorithm? And it turns out for these problems, there is really not much better. There are some slightly improved algorithms are known, but not a lot better algorithms are known for these problems. Okay. Now, so this suggests, we're going to, the title of this session is P, NP, and NP-Completeness. It's all about, we are not going to look at one problem, we're going to look at a class of problems. So let me write down what is P. P, in informal, I'm going to talk in informal term. All of this have very precise Turing machine definitions. Okay, you've seen theory of computation. You've probably learned Turing machines. This is a very formal definition, but I'm going to just stick to some informal definitions. So, what is P? P is a set of problems. P stands for something. So, problems for which there is an algorithm that takes time polynomial in the input side. Okay, so P stands for polynomial, and input size is an important thing. I'll come back to that in a minute. So what is a polynomial running time? So it can take something like 2n square plus 3n minus 5. Okay. You've all seen polynomials everywhere in your high school. So this is a polynomial in n. So any algorithm which is like this. So in particular, it's all bounded by some n power constant, 5, 10, 100, whatever. There is a constant. This is a constant. It doesn't depend on n. Any algorithm whose running time is bounded by some n power constant is a polynomial algorithm. Okay. So which of these problems belong to P? Is sorting in P? Yes? The running time doesn't look like a polynomial, n log n. But it is bounded by n square, right? Clearly. So it is polynomial. It's bound. I mean, all I want is the running time is upper bounded by. Okay, so it's the maximum time it takes is some polynomial in the input side. So it's it's bounded by n square. Clearly, log n is upper bounded by n. So all of these algorithms are in P. Max flow, shortest path, minimum spanning tree, longest common sequence, median, all of these problems are in P, whereas these problems, max click, PSP, SAT, I can't yet say they are not in P, right? Why not? I mean, all I said is, oh, here is an algorithm that takes 2 power n time, but there may be a better algorithm. I don't know that. Okay, at least at this point, I don't know whether these problems are in P. Okay, so that's your first class of problems. Now, as I said, what is a problem? Is there a mathematical definition for it? Yes. These are all. I mean, a formal definition would be languages that are accepted by a deterministic Turing machine in polynomial time. Okay, that's the formal translation of it. So, this is not some very loose statement, but in the language we have been talking about, this should help you understand what this is. Okay. Now the next question is, why do I care about polynomial, exponential? Why? I already gave you an indication on 2 days ago when we talked about Fibonacci recurrence relation. I said it's an exponential algorithm when n is 1000. Did anybody try that? I said, please go and try. Take a recursive algorithm, implement it, and see how much time it takes for small values of n. Okay, so it's a 3-line code. Write the code in whatever language you have, but write a recursive program. Try various values of n and see up to what value of n can you really go and get the answer in 5 minutes or 10 minutes when you sit. Okay, so if you have not, please do. So that the point is that exponential algorithms are bad for the following reason. So here is a table. So this is a table which tells you if you have an algorithm which takes n cube time, let's say, and if I run it on a problem of size n equal to 60, then the algorithm will take 0.216 seconds. Actually, this is from a book which was written in 70s. So today's computer, it may not be 0.21 second, maybe 0.1 second, something. Because computers will become faster. But if you have an algorithm which takes 3 power n time, you run it on a problem with n equal to 60, that's going to take you 1.3 into 10 power 13 centuries. Okay, today's computers are faster, so it's not 10 power 13, 10 power 11 centuries. Doesn't matter, really, right? 1.3 into 10 power 11 centuries to solve a problem of size 60 with your 3 power n algorithm. Okay. Computers have become powerful, but n has also increased, right? Your data you are handling is also increased so much that n is a trivia. 60 is a small number. When you just go back to the next column of this table and talk about 70 and 80, it's humongous running time. I mean, I showed you last time, right? 2 power n running time, when n is like 100, it's going to take you several centuries in modern computers. Whereas if you have an n cubed algorithm or even an n power 5 algorithm, yes, it's getting progressively slower even on a problem of 60, but it is still, we are talking about seconds and minutes. But when you talk about exponential algorithm where n is on the exponent, then it just zooms to really centuries. Okay, so this is one of the reasons we are all interested in polynomial algorithms. Algorithms that take polynomial time, that is associated with feasible computation, something which you can really solve in practice. So this table is very illustrative. It strikes you because somehow we have this image that computers are all powerful, they can do anything, everything fast. That's not true. Okay, this exponential growth is mind-boggling. So for a problem of size 40 on a 2 power n algorithm, it's going to take you 12.7 days. In those computers, right now it may be taking you 8 days instead of 12 days, but it doesn't really matter. Another illustration of the same table is that if you have an algorithm which takes n cubed, and in 1 hour, the problem size, let's say you can handle is like 50, let's say n3 is 50 in 1 hour, then if your computer becomes 1000 times faster, you can handle like 500, problem size about 500. Okay. But if you have an exponential algorithm, today if you can handle a problem size of 10, even if it becomes 1000 times faster, you can handle a problem of size 17 or something. Okay. So exponential algorithms are really bad. But these problems are appearing in practice. You really, in industry people scheduling, complex scheduling problems, they all come up in practice and you really want to solve them. So if you come across such a problem, you don't want to go and tell your boss this, that I can't find an efficient algorithm because I think I am just dumb, right? What would be ideal is that you should be able to go and say, no, I can't find such an algorithm because no algorithm is possible. In other words, if you come across a max click problem, and if your problem size is like 50 or 100 or something, currently you have only a 2 power n algorithm, and we saw this big table, the 2 power 100 is going to be centuries. You have to solve it. Okay, so what you can go and tell your boss, ideally, this is some wish list, is that 2 power n is sort of a lower bound for the problem complexity. Not only I can't solve it, there is no better algorithm for this problem, but unfortunately we are not able to say that as well. That's what makes this a conjecture, an open problem. Very important open problem is, can you actually come up with the polynomial time algorithm for these problems is a major important open problem. But what you can say is this. Okay, I'll come to the next slide later. So that's sort of the story. Now that's P class of problems, why they are important, why do we define P? Okay, one thing is that even an n power 100 algorithm is also called a polynomial time algorithm because it's constant, right? Okay, so that doesn't seem very reasonable because even that's going to take you a long time. But in practice, what we have seen in the last 50 years of algorithms is that somebody tried to prove that there is a polynomial time algorithm with running time n power 10 or something. Within the next couple of years, it gets improved to n power 8 or 7 or 5 or n cube. So typically, there are not too many problems. Maybe you can count 1 or 2 problems where problems that belong to this class with such a big complexity. Most of them have something like an n square and n cube running time. So this class is roughly associated with something which you can solve in practice. Okay. So that's the class. Any guesses? No, it's not. It's not polynomial time. It actually stands for non-deterministic polynomial. So this is a new nice concept again. You would have seen in the theory of computation course. So here we are going to, okay. So now I'm going to make a little more refinement here. For some reason, we are going to be talking about decision problems. What are decision problems? These are problems for which the answer is yes or no. Okay. So all of this, they are not decision problems. Find the max click. But you can actually convert them into a decision problem. It's not very hard. Right? If you want a max click in this graph, I can simply ask, is there a click of size 23? Right? That's a decision problem because the answer is yes or no. Now I can ask several such questions to an algorithm which solves a decision problem and find the max click. Suppose I really want to find the maximum click. I want to phrase it as a decision question. Then you simply ask, is there a click of size n, n minus 1, n minus 2. The first time you get an answer yes, you know you got your max click, right? Because you got no for all other numbers. So decision problems, restricting to decision problems is not such a big restriction. Again, for this theory of NP-completeness, we are going to restrict it to decision problems, which is good enough usually for practical purposes, because for a TSP, I want to know what is the smallest cycle you can get. You can convert it into, is there a cycle whose weight is at most some number? So try all possible these numbers and you will be able to answer the optimization problem using an algorithm for decision problems. So it's okay to talk about decision problems. Okay, what is NP? These are decision problems whose S answer can be checked in polynomial time given a proof or a witness. Again, the formal definition is languages that are acceptable by a non-deterministic Turing machine in polynomial time. Okay. So if you know what a non-deterministic Turing machine is, that definition should make sense to you, so you can be happy with that. But the informal definition is the following, that that if your S answer, if somebody gives me an S answer and a proof, then I can verify in polynomial time. Such problems belong to the class NP. I'll give you some examples. Okay. So let me write, we've listed a lot of problems. Let me list one more problem. Given an integer, is it composite? Yes. You all know what a composite number is, right? A number which is not a prime number is a composite. Is it a decision problem? Yes, because the answer to this question is yes or no. So we want to solve this problem. We want to come up with an algorithm for this question, that it takes a large number, 100 digit, 200 digit, 300 digit number. Somehow this algorithm should run the number, check something, and come back to say whether it's composite or not. Okay. Now we don't want to worry about polynomial time or not. I'll come back to that later. But I want to check whether it is an NP. Okay. That means, so I give you this 100 digit number. I give you several days to go and check whether it's composite. You don't care how much time you take. You want to come back and say yes, it is composite. How will you convince me? So the S answer should be checked in polynomial time. So I give you this number, 500 digit number. You spend 5 days. This is what happens in assignments, right? So you work hard, and as a teacher, I don't have too much time to check. So now you have to convince me. You have to write a proof, and I want to be easily check this. So 200-digit number, you come back and say, yes, it is composite. How will you convince me? Give a divisor. You say 243 divides this. Can I check it? Yeah, that's one division. I can do division. Okay, so that's a polynomial time computation. So that is the problem whose S answer can be checked in polynomial time given a proof. The proof here is a witness, a factor. Let's do another example. Hamiltonian cycle, right? The TSP, right? I asked the question, here is this weighted graph, distances on the edges, and I ask you, is there a traveling salesperson tour? A tour which starts from a vertex, go to every other vertex exactly once, come back, and whose total cost is less than or equal to 483. Okay, that's the question. Right? It's a decision problem. I give you this graph, you spend 50 days, come back, you say, yes, there is a tour. How will you convince me? Show the cycle. Oh, here it is from 1, go to 7, to 2, 3, 5, 8. And then what do I have to check? Weight. I just check the weights, make sure that these edges are already actually present in my graph I gave you. Check the weights, add them all. Addition is something I can do, right? So this is a problem whose S answer can be checked in polynomial time given a witness or a proof. Okay? So composite, TSP, all of these problems belong to this class N. Okay? So important thing is how much time did you take to figure out this cycle? I'm not talking about this. How much time you took to figure out this divisor? I'm not measuring that. All I am saying is if you have a proof, there is a polynomial time verifiable proof, a polynomial time so this is all about verification, right? That's what I mentioned in the first slide, that this whole thing is about finding solutions and verifying solutions. Okay. So now here is another interesting important observation. P is contained in NP. Do you agree? Well, again, if you are familiar with the non-deterministic Turing machine, deterministic Turing machine, you know that, oh, non-deterministic Turing machine is even more powerful. So anything you can do with the deterministic Turing machine, you can do it. So it follows. But let's stick to this informal thing, right? So suppose there is a problem like, shortest path. Is there a path from here to there of length at most 25, something like that? I give you this graph and you come back and say, yes, there is a path. You can give me a witness. But I can even ignore your witness because I'm a polynomial time machine. So in polynomial time, I'll actually solve the problem and check whether it's a yes or no. So you can even, I don't even need a proof because the whole problem is solvable in polynomial time. So I'll take that polynomial algorithm and run it and check the answer. So the S answer can be easily verified in polynomial time if the solution can also be found in polynomial time. So that's what it means by this whole class P is contained in N. Okay? The big open problem is what about the reverse? Okay, so this has actually $1 million prize from an institute in Boston called Clay Mathematical Institute, which a few years ago came up with important problems in mathematics, and they came up with $1 million prizes for solving each of them. This problem, which is exactly this problem, is every problem where you can verify in polynomial time, where there is a non-deterministic Turing machine, which will run in polynomial time and give you the answer, S answer. Can you actually also find the solution in polynomial time? This is an important open problem, and that's the problem for which there is a $1 million prize. Okay. Now, I already mentioned problems. Actually, I already mentioned problems which are here but not here, right? This is one problem. traveling salesperson problem is one problem where if I give you, the S answer can be easily verified in polynomial time. And I also told you that the best algorithm so far is exponential time algorithm. So it's not in P. So haven't we solved the question? That I have given you a problem here, which is not here. So we are done. We should go and get the $1 million, right? What's the problem? Sorry? Exactly. I just told you that current best algorithm is exponential. I did not tell you that it is not in P. This is not enough evidence to say that this problem is not in P. Right? This is the other slide, right? We would like to say this. We don't know. We would like to say this, that because no such algorithm is possible. If you can say that, then we would have said that, oh, this problem is an NP, no polynomial time algorithm is possible, so we are done. Now that's the hope, that's the conjecture, that these problems are hard problems themselves, that any algorithm should necessarily take more than polynomial time is the belief, the conjecture, but we don't have a proof of it yet. Okay? But what we do know is this notion of NP-completeness. So let's get to that. Okay, so let me use this. Okay, so we know that all these problems are in polynomial time. These problems are, if I appropriately phrase it in a decision problem, they all belong to the class NP. Okay, what is so these are problems in NP. So you're always talking about decision problems. But before I get to this, I forgot to mention this input size. I said I will tell you about it, right? What is input size? When I wrote down the definition of P, I said these are problems which are solvable in time, polynomial, in the input size. What is input size? Okay. So input size is basically you take your input, whatever is the input. If it's a graph, then a representation of the graph is your input. If you're trying to do sorting, then take the n numbers, write them in binary. Take an efficient encoding of the input, and the length of that encoding is the input size. Okay. So when it comes to network flow, for example, you have graphs, you have vertices, edges, there is weight numbers on the edges. Collect them all, write them in a binary encoding, and take that size. The length of that encoding is the input size, which may not necessarily be, we said, oh, if you want to sort n numbers, I've been loosely using n as the input size. It may not be n, but n times the length of the encoding of each of these integers. Okay? So the real place where it plays a role is, let's say I come back to this number, right? Okay, so I can erase it. Let's look at the question. Given n, is it prime? Okay, it's the same as, is it composite? We already thought, well, at least I said, for composite, I said it is an NP. It's not that easy to show the primes is an NP. How will you convince me that it is prime? Think about it, it is not that easy, right? I give you a whole 10 days to check it out, and you come back and say it is prime, it has no divisor. There's no easy proof of it. Right? It turns out there is, using some nice number theoretic properties, Fermat's little theorem and various things, one can give an NP proof of it, but let's keep that aside. Now, can somebody give me a simple brute force algorithm for this? How do you check? For I going from 2 to square root of n, if I divide n, then return false. When you come back and you survive, then you say return true. Okay? You just check from 2 to root n, any of these numbers divides this number. Why only root n? Don't you really have to go all the way to n minus 1? Right. So, if the number is composite, it will have a divisor within root n, right? Because if it is composite, it is a product of two numbers. It is not possible both of them to be bigger than root n, because then the product will be bigger than n. So, at least one factor should be less than or equal to root n. So, go up to root n, check whether there is a factor. Now, what is the running time of this algorithm? Square root of n, right? Square root of n divisions. We are doing, when you say running time, we are talking about some basic CPU operations. In this case, it's a division. It's about root n time. Is it a polynomial time algorithm? Yes, no? Yes, right? Okay. Actually, it is not. Because what is the input size here? It's not n. If I write n in binary, how many digits do I need? Log n to the base 2 plus 1. So, let us say roughly log n. So, the input size is not the number of values. In fact, if you take the number of values, then the input size is actually 1, right? So, it's very funny. You know, when we took sorting, we said there are n numbers, n was the input size, then 1 should be the input size here, right? There is only one number. So, the input size is actually your length of an efficient encoding of the number. So, it's log n. If log n is the input size, then what is root n as a function of log n? Right? So, if I take n, which is the input size as log n, then square root of n as a function of n, what is it? 2 power n by 2 actually, right? 2 power n by 2 is 2 power half log n. So, it's 2 power log n whole power half, 2 power log n is n, so square root of n. Okay? So, square root of n is the running time, but as a function of the input size, which in this case is capital N, it's an exponential algorithm, 2 power n by 2, right? N is n, because what is the motivation here? If I want to know whether it's a 50-digit number is prime or not, a feasible algorithm should take polynomial in 50, not polynomial in the value of the number, because that is huge. Hmm. 100 digits. In binary, it's 100 log 10. Yeah. So 300 digits. So that's why if I want to know a 10 power 100 kind of a number is prime or not, and if the algorithm takes proportional to 10 power 100, that's not a good algorithm for me. A polynomial algorithm, what I want is a number which is polynomial in the size of the input. The size here would be like 100 log 10, which is about 300. Okay. So that's sort of a side digression on the input size, which plays a role in this kind of problem, but not so much in the kind of problems we have looked at. So if we are looking at a graph problem, the input size will be like n square. Okay. The adjacency matrix representation is the input size. Okay, there is more story on this. So it was a major open problem whether there is a polynomial time algorithm to test whether a number is prime. Right? We saw that this is not a prime polynomial time algorithm because this is exponential in the input size. So a polynomial time algorithm should actually take polylog time, log square, log cube, log power 4 time. Okay, this is this is a big open problem since people started looking at numbers and primes, hundreds of years old, and the solution for it came from India. IIT Kanpur, Manindra Agarwal in 2002, I think, came up with the he and a couple of his undergrad students came up with a polynomial time algorithm for testing whether a number is prime. So polynomial means poly in log n. Okay. And it's called primes is in P. So you can just look up in Google primes is in P or Manindra Agarwal. You will see this algorithm, and it uses a good amount of analytic number theory, algebraic number theory, some good number theoretic properties, something about polynomials and various other things to come up with an algorithm which takes something like log power 6. At that time, it's been slightly improved now. So that's a polynomial time algorithm for testing whether a number is prime. If you can test a number is prime in polynomial time, you can also test compositeness in polynomial time, right? Because it's sort of like a deterministic Turing machine which comes back and says yes or no. So you will also get the other answer. Okay, so that's the story of, about big Indian contribution in this P and P notions, and an important note about input size. Okay, now let's get to NP-complete problems. So as a picture, what we saw is, P is a class of problems, and we saw that P is contained in NP, so NP is like this. And NP-complete problems are problems in NP, so it's problems which are sitting here. I mean, I shouldn't draw these pictures because we don't even know whether there is anything here at all. It may be the same picture, but let's say NP-complete problems are problems in NP which are somehow hard, most difficult problems in NP. That's what it is. What does that mean? These are problems. So here is a problem. Let's say SAT, which I've written down here. Given a Boolean formula, is there a satisfying assignment? It's one of those NP-complete problems. What does NP-complete problem means? That every problem in NP, let's call some P1, P2, these are all maybe Phi 1, Phi 2. A lot of problems which are in NP, they all reduce to this problem in polynomial time. Problems in NP to which every problem in NP reduces in polynomial time. What does reducing mean? Well, if this problem is solvable in polynomial time, then using this reduction, using this algorithm as a subroutine, we can solve every problem in NP in polynomial. Okay, this looks like a complicated notion. It simply says that, okay, we'll see some examples. So a reduction, okay. So for example, sorting reduces to finding min. Let's look at in the polynomial world, what does reduces to? By that what I mean is that if I have an algorithm for this problem, I can use that as a subroutine to solve this problem. Do you agree with that? Right? Suppose I have an algorithm which we give a list of n numbers, it will find the minimum. Can I use it as a subroutine to sort? How will you use it? Yeah, pass a different list, right? Take the entire list, give it to this algorithm, it will give you the minimum, remove it from that list and give it again. It will find the next minimum, remove it, it will find the next minimum. And how much time? So you just have to call this something like n times. Call this n times. So if you solve this, you can multiply by n and you get a running time of this. I mean, there may be better ways to do it, but all I'm saying is if using this as a subroutine, you can solve this. So that's the kind of a flavor that if you have a polynomial time, so remember the big open problem is we don't know this, right? Now, what this reduction or this notion says is that if you have a polynomial time algorithm for this problem, then you can use this as a subroutine to solve every problem in NP, use this reduction, use this subroutine, solve it in polynomial time. What does that mean? If there is a polynomial time algorithm for this, what does that mean to that question? Yes, right? NP is contained in P because this tells you that if you have a polynomial, this is, everything is loaded into the definition. Sometimes definition can be very artificial, right? Because you throw everything into the definition, the theorem will be easy to prove. Okay? And then you have to think about, is the definition meaningful at all? Are we saying something useful? We'll come to that. So all this is, so the consequence, the definition here is that, or a corollary of it, is that if an NP-complete problem has a polytime algorithm, then NP is contained. Why? Because that's how we have loaded the definition. Because we said that is actually the definition of NP-complete problem. Because every problem in polynomial time reduces to this. That means I can use this as a subroutine, an algorithm for this as a subroutine to solve every NP problem in polynomial time. So every NP problem will belong to this, and we would have settled this problem. So because of this reason, people believe that NP-complete problems are hard. They do not have polynomial time algorithms, because the general belief in the theory community is that this is not true. That there are problems which are, this is also intuition, right? You don't expect solving the problem and verifying the solution to be of the same complexity. You expect solving. The student's work is harder than the teacher's work, right? So you expect solving the problem will take more time than actually verifying it. So the belief is that, there will be problems where it's easy to verify, but it will be harder to solve. So this is the belief. And we have some evidence that here are these problems where people have tried hard, they're not able to come up with a polynomial time algorithm. So these are witnesses for these problems. But we know more. That, okay, so this is the corollary. If an NP-complete problem has a polynomial time algorithm, then NP is contained in it. Now, it's okay to have a, very nice definition of a class, but is there some problem at all here in this class? Right? If this class is empty, then this definition makes no sense. Is there, where is an NP-complete problem? This is all fine saying every NP problem reduces to this, but is there even one problem of this type? Do we know this, right? And this was a big, big contribution from Stephen Cook and Levin in 1971. And they showed that SAT is NP-complete. Okay, so this problem, not exactly this version of SAT, they looked at even more general version of SAT, where they showed that this problem is NP-complete. Okay? At that time, even this notion of NP-completeness was not there. The title of that paper is something like the complexity of theorem proving procedures or something. Very, and later the whole community. So so how did he show this, right? It looks like a very hard thing to do, because you are saying every NP problem in the world reduces to this SAT problem in polynomial time. So you have to just go and find all, it's hard enough to show this specific example sorting reduces to min. Now you're going to pick every NP problem reduces to this, right? Well, how did you show this? Well, there is a definition of an NP problem. What is an NP problem? there is a non-deterministic Turing machine which accepts in polynomial time, right? So what he took, how did he show this? That he took a non-deterministic Turing machine. So there is a pi, a problem in NP. So it has a non-deterministic Turing machine which will accept in polynomial time. So Turing machine, we all know how they work. So there is this finite set of states, there is transition function, there is symbols, you know. Now he took all this Turing machine and modeled it as a Boolean formula. Okay. So there is a variable for every state, every tape, symbol, every transition combination, all kinds of Boolean variables he created. And he said this Turing machine computation starts with your input x, and non-deterministically it will stop and say yes. If so, this computation sort of gave a satisfying assignment for this formula, and he said, you know, this Turing machine computation can be modeled it as a formula such that this formula is satisfiable if and only if on this input this Turing machine will stop and give an yes answer. Which means that if you can solve SAT in polynomial time, every problem into a NP by definition has a non-deterministic Turing machine which can be modeled as a SAT. You can solve every problem in NP in polynomial. Okay. Now, as I said, this corollary tells you that if you want to show, and the corollary and this belief tells you that if you want to show that some problem is not polynomial time solvable, try and show it is NP complete. Right? Because if you show it's NP complete, then you know that it is one of these hard problems. There are lots of such hard problems, and it still doesn't prove anything that there is no polynomial time algorithm, but it is sort of a candidate problem that if you show this polynomial time, then you know many other problems also in one shot become polynomial time. So this you don't expect it. So the common notion of algorithm designers, when you come across a complex engineering problem, you try coming up with polynomial time algorithm, and if you fail, you try and show it is NP complete. And trying to show NP complete means that you believe that it does not have a polynomial time algorithm because it has a big consequence if there is. Okay. So now, how do you show something is NP complete? Well, the definition says that you take every problem in NP and reduce it in polynomial time. That sounds like a very hard thing to do. In fact, today I will give you examples of trying to prove some problems NP complete. Okay? We will not do it because next year, after this paper in 1972, Karp realized that this is actually a gold mine paper, and he showed a lot of problems, TSP, click, vertex cover, various things NP complete. Again, at that time this notion was not there, but essentially what he showed is NP. And how did he show? He did not take every problem in pi and showed that reduces to this problem. He simply took SAT and said SAT reduces to this problem. Right? Because Cook has already done the hard work to say that every problem in NP reduces to SAT. So he started from SAT and said, okay, SAT reduces to click. What does that mean? That if click has a polynomial time algorithm, then so will SAT. And Cook has already shown that that means that NP is contained in it. Okay? Well, he doesn't even have to pick SAT. He also derived some problems. He can pick any problem which is NP complete and reduce it to it. Right? So that's how you show something is NP complete. What do? You take a known NP complete problem and reduce to your favorite problem which you are trying to prove NP complete in polynomial time. Okay, that's important. That if essentially to show that if you can solve this in polynomial time, you can solve it. We will actually see some couple of examples today, then you'll get a flavor of it. Okay, so that is the so both Karp and Cook and I think Levin all got Turing Award for these results. Turing Award is like the computer science Nobel Prize, and all of these people got Turing Award for this notion of NP completeness. It's like an interesting somehow, that we are not able to say this. We are not able to prove lower bound for problem saying, oh, any algorithm should take more than polynomial time. That would be a nice settling of it. But NP-completeness brought an intermediate theory. So what we can say is this, that I can't find an efficient algorithm, but don't fire me and hire somebody else, because none of these famous people can also give a polynomial time algorithm for this, which is same as saying this problem is equivalent in some sense to this whole lot of problems which people have proved in NP-completeness. Okay. So with this notion of NP-completeness, you can say at least this much and save your job. Okay. Now let's see one example. We have time for break, right? So we'll do at least one example of NP-completeness reduction, and and then the next session is about what do we do, right? These problems are practical problems. Currently, they are exponential time algorithms known, and they are NP-complete. Is at the end of the story. You can't go to your boss and say, I can't find an efficient algorithm. Nobody can find an efficient algorithm, so this problem doesn't exist. No, of course it exists. It needs to be solved. You need to do something about it. That will be the topic for the next session after the break. Okay. So now I'll give you 2-3 examples of how do we show something NP-complete. So let's get a polynomial time reduction from stat to click. And this is again, pretty interesting. It's all about connecting problems. I mean, we know min and sorting are somewhat related, okay, but this is like finding, you have a Boolean formula and you want to set variables so that whether it is satisfiable, and here you have a graph and you want to find a set of vertices that are mutually pairwise adjacent. How do you relate these problems? That was Karp's genius, and now it's become a routine thing for people to do this. Okay? We even ask this as an exercise in interview question or exam question. Okay, so let's see what is the input here. So what is the problem here? The input is some clauses, and there are these variables. These are variables, these are clauses, F, and these are variables. So each clause would be like so let's actually draw it for one example. Okay, so this is my formula. So these are the and we want an algorithm to say whether the formula is satisfiable or not. And you have a subroutine which, given a graph, will tell you whether there is a click of some size or not, right? So here, what is the input here? There is a graph G and an integer K, and the question is, does G have a click on K vertex? Somehow, if you have an algorithm to solve this, you want to say that you can use this as a subroutine to solve the satisfiability question in polynomial, which means that I have to take my SAT input and model it as a graph, right? That's all I have to do. So what is the goal? For this formula, I want to construct some graph G and some K prime. I will do it with the following property, that F is satisfiable if and only if G prime has a K click. and I want to do this in polynomial time. Some transformation, we want to take your input Boolean formula, transform it to a graph with the property that if there is a k click, then k is also your choice, right? You will come up with your k, some k prime. From the so this graph and the k prime depend on this formula. So given this formula, you construct this graph and the click some parameter and say, okay, you said you have a subroutine for click, solve it on this graph and tell me whether there is a k click. Based on the answer, I will get the answer for this because my graph is constructed with this kind of a property. If you say yes for your click question, I will know that f is satisfiable, and otherwise I know f is not. So this is exactly what it means by a reduction from one problem to another. So we take a known NP-complete problem. This is always important, that you don't take this problem and reduce to a known NP-complete problem. This is another thing where students do a lot of mistakes. We take a known NP-complete problem, reduce that to this problem, because the consequence what you want is that if this has a polynomial time algorithm, then you can solve that in polynomial time, but you know that you've already shown that that is NP-complete, so this will be. Okay, so let's see how I will do it, right? So I have to construct a graph now with this property. So I will, for these, there are 4 clauses here, so I will construct, this is my vertices of this graph. Okay. I'm doing it for this example, but you should get the general picture out of it. This is my vertex set of this graph from the formula, and how are the edges? Let's initially, as a false start, let's say I draw all edges between every pair of them. Okay, so every edge inside, it's all independent, and every edge between every pair is there. Remember, my goal is this. This is what I want to achieve. What is k? The k prime is going to be number of clauses. So when I do this construction, I have no idea whether this f is satisfiable or not or anything. F is some arbitrary formula. I construct it, transform it to a specific graph with the hope, at least this is the purpose of my transformation, that the click problem on graph is equivalent to satisfiability question on the formula. Okay. Suppose I do this, then, and suppose f is satisfiable. F is satisfiable means that there is some assignment to, so every clause is satisfied by some variable. So I pick that corresponding. So maybe x1 satisfies this, maybe x3 bar satisfies this class, maybe x4 satisfies this, and x1 again satisfies this. So I pick, if f is satisfiable, there is a satisfying assignment, every clause is satisfied by some variable. I collect those variables and they form a 4 click. 4 is the number of clauses here. So if f is satisfiable, there is a 4 click, because of the way I constructed my graph, there is an edge between every pair of these sets. But is the converse true? Suppose there is a 4 click, I want to be able to make sure that f is satisfiable. Can I reverse this argument which I just said? Right? Can I reverse this? Well, let's try. Suppose there is a 4 click. Can it pick 2 vertices from the same set? Why not? No, it might pick 2 here and 1 here and 1 here, and it may not pick 1 from anybody at all. Well, the graph has a 4 click, right? This is a graph. I want to say that if the graph has a 4 click, it has to be of a particular type from which I want to be able to pull out a satisfying assignment for the formula. That's my goal. So the 4 click can be anywhere, however, where I have no control. Right? I gave it to this subroutine and said, here is a 4 click. The question is, can the 4 click have two vertices from the same set? There is nothing to do with class. No, no, no. Let's see the way I constructed the graph. How did I construct the graph? I said, did I draw any edge at all here inside? No. The way I specifically constructed the graph is that the edges are only across, right? So a click means that every pair of them is adjacent. So I cannot have two vertices from one set in the 4 click. Because I did not, there is no edge between these two. A click means that this is a subset of vertices where there is an edge between every pair of them. So I cannot, there must be one from here, one from here, one from here, one. No, but I made multiple copies. Remember, don't think of it as this is an X3 for first class. This is an X3 for the third class. This is an X3 for fourth class, and so on. So think of them as sort of a different. So I made copies. Yeah, an X3 here and X5 may be adjacent here, but that's actually I should just simply call this as X11, X31, X41, X22, X32 bar, 3. So these are like different set of variables. Okay, so 4 clicks should necessarily contain one vertex from here, one vertex from here, one vertex from here, one vertex from here. Can I always translate it into a satisfying assignment? Right? So here is an attempt for a satisfying assignment. Let's watch. Let's see. So yeah, you may have gotten what I was going to tell you, but let's see. So here is my attempt to get a satisfying. I just construct an arbitrary graph. Okay, how much time have we taken, right? So I'm promised poly time. That's no problem, right? The running time is like an n square or something. So yeah, I duplicated, but the size of the formula is the total number of variables, right? Including if a variable appears here and here, it does contribute to the size separately. So I have this total size and I've spent some n square time to construct this graph. So polynomial time computation. But you'll see a problem here when I revert back to a satisfying assignment. Suppose, so this 4 clicks. So I want to prove this. This is what I want to prove. Right? If I prove this, then it's fine because then I can use this subroutine to solve that thing. So if f is satisfiable, I already gave you a 4 click. You figure out who satisfies this class. I take that variable from here. Who satisfies the second class, take that variable from here and say that those 4 are adjacent the way I constructed the graph. So it's a 4 click. But conversely, if I have a 4 click, here is my proof and it will have a problem with it. Okay? So then we will come back and adjust the graph. The proof is, pick the vertex that is picked from this side and set it to true. Remember, I have to give an assignment to satisfiable. So that will satisfy it. Pick whichever vertex you pick from here and set corresponding. If it is an X3 bar, then set that X3 bar to true, which means X3 to 0. Set that to true. Set this to true. Set this to true, and that will satisfy every clause. So it's a satisfying assignment. What's the problem with that? Is that a problem? Suppose you have a variable x1 here and another x1 here. That's fine. I said x1 to true and I said x1 to true, which is fine. If I had an x1 bar here, the 4 click, suppose, in fact, 4 click is always there. If you look at this graph, there's always a 4 click, even though if it is not a set. So if I choose an x1 here, the 4 click, right? I did not choose it. This algorithm, subroutine, which I gave it and said, give me a 4 click, picked up an x1 here, an x1 bar here, and x4 here, and something here. Now my satisfying assignment, I'm saying, set x1 to true, set x1 bar to true. I can't do both together, right? There is a problem. So now my solution is, I have no control how the click will pick, what kind of a click will pick. I will go back and change my graph. This is where I have the control because I took the formula in polynomial time and construct the graph. So when I draw an edge, my edge adjacency is going to be different. I said Draw every, don't draw any edge inside and draw edge between every pair of them. No, not every pair of them. If I have an xi here and an xi bar here, don't draw that edge. This is my control at the beginning of the formula, right? I construct the graph. I have no idea what kind of clicks are going to be there, what the algorithm will pick, that's okay. But I construct the graph, so I am going to give a reduction, take an arbitrary formula, construct this graph, no edges inside, cross edges, if there is an xi here and an xi bar here, don't draw that edge, otherwise draw every other edge. Every other edge across you can draw. Now, this statement is true. The same proof, f has a satisfying assignment in every clause or something, that will form a click, because whatever is setting true and whatever is setting true, they cannot be negation of each other. So, there will be an edge, they will form a 4 click. And conversely, okay, if there is a k click here, it must necessarily pick one from each of it, and you can revert back and you will get a satisfying assignment for the first. Okay, so it's very, it is actually simple, but in 70s it required a paper with, paper did not contain just click, it had a lot of other problems. There are some 20 problems where they are shown in NP-Completeness. Let's do one more simple example now, which you should be able to get it, and then we will stop for a break. Let's define which is the conjunction of disjunction to the click problem. You can ask something similar to click, which is called an independent set. So, what is an independent set? Again, input is G, some integer k, and the question we are interested in is, does G have an independent set on k vertices? And what is an independent set? This is a subset of vertices such that no pair of them is adjacent. Okay, so here again one is interested in the maximum independent set. It's very similar to click. So, I have the 7 vertex graph. Can you give me the maximum independent set in this graph? This is a set of vertices where between any pair there is no edge. For example, the set 1, 3 is independent. There is no edge between 1 and 3. Is there a larger independent set? 1, 2, 5, 7. Is it independent? No, because 1, 2 is an edge. One, 3, 5 is independent. Yes. 1, 3 is 2, 4, 7. Is there an independent set of size 4? Probably not. So, the maximum independent set size is 3. Okay. So, this is the question. I mean, if I remember, I was talking only about decision problem. Maximum independent set is not a decision problem, but the way to phrase it is there an independent set of size 4 or size 3? So, that's this problem, right? So, I give you a graph C and an integer k, and I want to know, is there an independent set on k word? This is also an NP, right? Because if the answer is yes, you can give me a proof which I can verify easily. There is an exponential algorithm, try all subsets of vertices, and I want to show it as NP complete, right? means that if you can solve this in polynomial time, some other problem which we have already seen NP-complete will be solved in polynomial. So can you give a reduction from a known NP-complete problem to this? So this is looking similar to what problem? C. You solved weighted independence at CP? That was a scheduling problem, no? Are you referring to something I talked about or somebody else? It can be reduced. So you would not have solved weighted independence. You are referring to some other problem. Which, I mean, did I talk? No. Yeah. Yeah, okay. Maximum contiguous sum and so on. They are not related to this independence set problem. So, I mean, think about it. See if you can model it as a graph. So this is a problem on graphs, right? You have a graph. Think about drawing edges and see what you mean by independence set and what is the maximum. See, we will get to the next session where I will tell you what you can, what you can do with problems being NP-complete. So what it means by NP-complete and all that. But we are talking about a general graph. That graph may not be a very general graph. This is a general graph, and if you want to know whether the problem, find the maximum independence set, NP-complete, and it is similar to what problem? Click problem we have seen. Can you think of a simple reduction from click to this problem? So suppose somebody says I have a polynomial time algorithm which can solve independence set. Then you should be able to solve click in polynomial time. How will you do? They're very related. Click is all about mutually adjacent and independent set is about mutually non-adjacent. So, can you do a inverse? What? Yes. Take the complement of the graph, right? There is a notion of graph complement, right? Graph complement is whenever there is a non-edge, you add an edge. Whenever there is an edge, don't add an edge, right? So, I want to solve click problem. What do? I take this graph, take the complement of the graph. That's a polynomial time computation, right? You go to your adjacency matrix, change the 1s to 0, 0 to 1, what you get is a complement graph, right? That's an n square step. So, take the complement graph and give it to this and say, can you give me a k independent set? So if you can solve this in polynomial time, you can solve click in polynomial time if there is an n square reduction. So you just solve in the complement graph the independence set problem, you will get click solved. Okay. So this is all about, this NP-completeness reduction is all about connecting between problems, right? This requires a different kind of thinking. The whole course, what we've seen so far is, given this problem, what technique can you throw at, divide and conquer, greedy, or NP, dynamic programming to solve that problem? Here, this problem is looking similar to what other problem, that's the kind of thinking. It's similar to click. A click in a graph is the same as the independent set in the complement graph. And, this complementation is just an n square time. So it's very important that sometimes you may actually do reductions, but it may not be a polynomial time. But in this case, it's polynomial time reduction. So what we saw was stat can be reduced to click, right? This is take the formula and construct that kind of a graph. And click can be reduced to independent set. And then the industry of NP-completeness went on in all kinds of directions. Now we really have thousands of NP-complete problems. Okay? That makes life harder to show something is NP-complete, because If I ask you to show independence that is NP-complete, so far we know only these two problems, so you just have to try. But now there is a pool of thousands of problems which are NP-complete. So when a new problem comes and you believe it's NP-complete, you have to figure out, oh, it is looking very similar to click or vertex cover or independence set or TSP or all that, and give a polynomial time reduction to your problem. Okay, so we will. That's hopefully you got a flavor of why this theory is important. It is related to this powerful long-standing conjecture. Why polynomial time is that class defined, because it is associated with feasible computation problems you can actually solve in realistic time. And what is NP, what is NP complete. So, so the picture is NP and this is P, and we NP complete problems are here, and we believe that they actually belong here. They are in NP but not in P, and that's what differentiates between P and NP. And yeah, so now this is all 71, 72, 73, 75 in the last about 25, 30 years. Apart from showing problems NP complete, there has been a lot of work on trying to deal with this NP complete problems and address this conjecture. I will give a survey of this after the break.